Now to the lecture, I would like to welcome Professor Mike Celia and thank him to kindly accept our invitation. Thank you very much, Mike. Before the lecture, I would like to introduce him to the audience, though you all agree he does not need any introduction. Mike is Professor of Environmental Studies at the Department of Civil and Environmental Engineering at Princeton University. He is also Director of Princeton Environmental Institute. He received his MS, MA, and PhD in civil engineering all from Princeton after finishing her Bachelor of Science Studies in civil again at Lafayette College. He then became a research associate and a lecturer at the same university in Princeton for about 3 years, but then moved to MIT as assistant professor of civil engineering for 4 years. But that stay at MIT made him miss Princeton so much that he returned back again to Princeton, first as assistant and then associate and finally full professor of civil engineering. During his appointment at Princeton, he has been program director of environmental engineering and water resources, program director of environmental studies, and chair of the department as well. Currently, he is director of Princeton Environmental Institute, as mentioned before. Mike has made many groundbreaking contributions in several scientific fields, among which I could just mention groundwater hydrology, geological sequestration of carbon dioxide, simulation methods for multi-phase flow in porous media, studies of methane leakage from abandoned oil and gas wells, and contaminant transport simulations also are those subjects that he's quite famous for. For his significant research and educational impact globally in the field, he has received many distinctions, over 30 awards, among which I could just highlight a few. Honorary doctorate degree from Stuttgart University is one, Distinguished Teacher Award from the University of Princeton University, and also elected to the US National Academy of Engineering in 2016, a code for contributions to the development of subsurface flow and transport models in groundwater remediation and CO2 sequestration. He has been also Darcy Visiting Professor at Utrecht and University of Eindhoven in Netherlands, honorary lifetime membership award of the Interpor, International Society of Porous Media. That's the most prestigious award the society offers. Elected fellow of the American Association for the Advancement of Science, and also elected fellow of the AGU, American Geophysical Union. Also, he has been Darcy lecturer. I remember myself when I was a graduate student at ETH, he visited us and it was quite an inspiring speech he gave at that time. He has been in countless committees, advisory boards, and award committees, including Total Scientific Advisory Board for CCUS, Carbon Capture and Utilization, Science Advisory Committee member of Environmental Molecular Sciences Lab of Pacific Northwest and Northwest National Lab, and review panel member for Earth Sciences Division at Lawrence Berkeley National Lab, and many more. His Google Scholar page lists most of his publications with over 16,000 citations in prestigious journals and diverse topics, from simulation, carbon capture storage, policymaking, and even just recently on electric power development. Please visit and study his work, which I do quite frequently and use them not just for research, but also my teaching. It's our pleasure and honor to host him as the first distinguished keynote lecturer of GeoScience and GeoEnergy webinar series. His talk will last for about 30 minutes. And after that, please kindly type in your questions. So text your questions, and Sebastian would go through them at the end of the lecture, and we will answer them all as much as the time allows. Mike, please, the floor is yours.
Thank you, Hadi. Very kind introduction. I'm going to share my screen. If you can't see the screen, you should yell out and let me know. Let's see. Delft lecture, this must be it. Here we go. Everyone can see a title slide, I assume?
Yes.
Good. All right. So thanks, everybody. I'll try to keep this to 30 minutes. So I'm just going to highlight a couple of things. And I'll warn you, this is not a technical talk, as you might imagine, given the title, although I'll say a little bit about some technical challenges that we're involved in at the moment. I'll start off with 4 simple comments. From my own experience, I would say that for the last at least 2 decades, right, there's been this prediction that a large-scale CCS industry is going to sorry, I'm just going to turn on some video here so I can see some of your faces. All right. Otherwise, I feel like I'm really talking into my computer. Okay. There's been a prediction, an expectation that large-scale CCS is going to develop. Almost every future prediction of energy systems assumes whatever amount of CCS is needed will happen, and oftentimes that's a large amount. But in my pessimistic days, which apparently was the case when I wrote this slide, I claim that I don't see much evidence that CCS industry is developing or necessarily that it will develop, which of course leads to the question that I pose as the title of the talk: does CCS have a future? And I thought I would attack this by, first of all, just giving you a couple of quick reminders about the current emission situation, remind you of some basic information about CCS, capture options, storage options, and a couple of quick words about capacity, meaning storage capacity, and rates at which we can actually access that capacity, which is what I mean by injectivity. And then the way I think about CCS these days is really under the heading of what I call the geography of CCS, because how I think about CCS in the United States, which is where I live, is completely different than how I might think about it for a country like India or for a country like China. So I think that if you're interested in practical aspects of CCS and you don't appreciate the geographical differences, there's not much chance of moving things forward in any significant way, in my opinion. All right, so just to remind you, this is time on the x-axis, CO2 emissions associated with fossil fuels on the y-axis. We're currently sitting at about 37 gigatons of CO2 per year. If you convert just to gigatons of carbon, getting rid of the 2 oxygen molecules, it's just around 10 gigatons of carbon, which is a number I can remember. 10 is a good number for me to remember. You'll see that in the financial crash of 2008, 2009, there was a downturn immediately followed by a significant rebound. What happens next year and the year after, given the COVID-19, remains to be seen. And in many ways, I think how we come out of the current downturn in emissions will probably tell us a lot about what our future holds. I would imagine that's going to be a good predictor. Anyway, if we look at the emissions by country, you know, there are sort of obvious things to see. First is China's, on a national basis, is by far the largest emitter. USA is second. EU is then following, and immediately below that is India. And I claim that if we can't solve the emission problem in all 3 of the countries I have circled, that we have no chance to solve the global climate problem. All right, and if we think CCS is going to be part of the story, then I argue as a corollary to that, that we should be looking at each of these places on its own and understand what the local challenges are inside each of those countries. All right. Just a reminder that IPCC, you see here in the box, from a 2018 report, IPCC put out a report recently about what needs to be done if we want to hit 1.5 degrees as the average global warming in 2100. All right, and these lines here are many scenarios that they looked at. I'll just remind you that the emissions here continue in gigatons of CO2 per year. This is a rapid decrease. You can imagine, you can all make your own determination of how realistic any of these is. But if you look at any of these scenarios, all of them will include some amount of CCS. All right, but what's more interesting for me is that the second half of the century, you get this enormous amount of negative emissions that have to happen. All right, like 10 to 20 gigatons a year of negative emissions in the second half of the century after this incredibly steep decline in the next couple of decades. And most of these negative emissions involve some version of CCS. All right, so even if CCS doesn't play an enormous role here, maybe only a few gigatons per year, when you get into the negative emissions projections, okay, everyone is relying on CCS. And so in some sense, we as a community, I think, have an obligation to be realistic and think about what's possible and at what scale can we implement CCS across the world and therefore locally by region and by country. Just to, this is one of the inserts from that report. BECCS here is bioenergy with CCS. That's the yellow part. You see this on this graph is taking up a little bit more than 10 gigatons a year by the end of the century. And this is agriculture, forestry, and other land use. I'll just comment that both of these, both the brown and the yellow in the negative emissions, all involve aspects of flow and porous media, either in the shallow zone, meaning the soil zone, or in the deep zone involving CCS. So if any of this is remotely true in regard to what we can expect, if nothing else, flow and porous media and geosciences should have a good future in regard to job opportunities. All right, so you all know what CCS is about. You capture emissions typically from a large stationary source, although it may not be the case going forward. Instead of emitting to the atmosphere, they get directed back underground into depleted oil reservoirs, gas reservoirs, or deep saline formations, or some combination of the three. It's the basic idea. I want to point out something that for what I'm going to say, in particular about the US, is important, and that is that there are different options for how we capture CO2. Okay, so capture from these gas streams. Some industrial processes have as their effluent essentially 100% pure CO2 stream, which means you don't have to do any gas separation, which is the expensive part, in order to capture the CO2. So this becomes, this 100% CO2 becomes the sort of low-hanging fruit, all right? And one might think logically that if you can use that to start a large-scale industry, that's what you should do, because it's the lowest cost for capture. Most point sources, like power plants, are a more dilute stream on the order of roughly 10%, which means you've got to do gas separation, which is the expensive part. I note here in this double asterisk, right, that something called the alum cycle has been proposed. It involves oxyfuels and sort of separation at the beginning, but this is a process where from a power plant, the exhaust stream is pure CO2. So the capture cost at the effluent part is as low as the first one that I circled. So if it were to work out, and this is a large-scale experiment being done right now, that we could imagine replacing, for example, the fleet of coal-fired power plants in the United States that's about to retire with natural gas alum cycle power plants. Okay, then we have an interesting possibility to capture large amounts of CO2 from the power sector. All right, so that's one of the hopes that sits out there. The last thing I'll mention is this direct air capture, which lots of people are interested in these days. You got to remember the current concentration in the atmosphere is about 400 parts per million. So now you're talking about an extremely dilute stream. And while I know that there are numbers that are being put out that make direct air capture begin to look appealing, I have to say I remain somewhat skeptical just because it seems like an enormous challenge to think about capturing that level of the level of CO2 we need from this kind of a gas stream. All right, I'm not going to talk about natural systems. They're interesting to think about, but not today. The last thing I'll point out is just that this idea of what I call a mixed system, bioenergy with CCS, right? This is the main mechanism for negative emissions, BECCS, where biomass will take CO2 out of the atmosphere as part of its growth process. You use the biomass instead of a fossil fuel for a power source, and then you capture the CO2 that would otherwise go to the atmosphere. So the vegetation is taking CO2 out of the atmosphere. Its combustion is not releasing it back because we're doing CCS, so you get a negative emission. All right, those are the capture options. Storage, I'm sure you all know, we have options for direct storage, either in deep saline aquifers, which have by far the largest storage capacity, or depleted oil and gas reservoirs. In terms of utilization, the U part of CCUS, basically it's EOR that we talk about. So either we're going to inject for EOR or we're going to inject for what I'll just call direct storage, typically in a saline aquifer. Give you a sense of storage capacities that are available. This is a paper that was put out by Ruben Wannis's group at MIT now 8 years ago. I think it's a great paper, looking at dynamic, meaning evolution over time. So transient estimates of storage capacity for, I think they did 11 or 13, I don't remember, but you can count the number of blue rectangles. Deep saline aquifers for which there was sufficient information, geological information, that they could make credible simulations. And they tracked pressure buildup, capillary trapping, dissolution trapping, all these sorts of things to come up with these estimates. So for example, you can look at the Mount Simon formation in the Midwest, which many people are interested in. You go to the Illinois part here, you get a capacity of 23 gigatons of CO2 storage after 100 years. All right, and if you add up all of these, I think you get about 170 gigatons on a 100-year timescale. That tells me that certainly in the US, we have sufficient storage capacity to allow CCS to be a major player if we can develop an industry to be a major player in regard to carbon reduction technologies. All right. So what's the current state of CCUS? I would argue the physics are sort of very well understood. Capacity estimates are certainly positive, meaning like we saw for the US, there tends to be optimistic estimates of storage capacity. Our work and other work, I think, shows that risks appear to be manageable, but we sit here with this expectation of sort of an ability to put 1 to 10 gigatons of CO2 a year underground, within the next 30 to 50 years. And I claim that will be difficult to meet. I know difficult is a word we're not supposed to use. I should put that it's a challenge to meet it, but the fact is it's a hard problem. I also will argue in the next couple of slides that near-term opportunities are quite different across the globe. And I think everybody agrees, they've agreed for the last 20 years, that now is the time for large-scale CCS to begin. I've heard that for 2 decades. It has not begun. So my question remains, how can this begin? How can we make this happen? Right? That's the question. So now I get into the geography part. US, China, India. If we can't solve all 3 of those, we can't solve the problem. So I'll say a few words about each of them in terms of what I think is most important. The one most important thing right now. All right, and I'll start with the US. I'd say the US is the most advanced in regard, and certainly among those 3, but I would say across the whole world, in regard to identification and characterization of good storage formations. We have a lot of experience with injecting CO2. Right now, about 60 million tons of CO2 is injected every year for the purpose of enhanced oil recovery. Now, that's great. The caveat to that is that 80% of that 60 million tons is not from anthropogenic sources, meaning it's taken out of the ground, piped somewhere and used, as opposed to being captured and used, right? So there's only about 20% of this that's captured from industrial sources. Almost all that is gas separation. In any event, I claim here the next step is large-scale infrastructure development and investment and development. Okay, and I'll tell you what I mean by that in the next slide. But this is motivated by the fact that the U.S. now has something called the 45Q tax credit. All right, well, it's had it for a long time, but in early 2018, the money involved with this tax credit went up significantly. So right now, this 45Q tax credit says that if you fit within the time parameters, which I won't go into, but you can receive a tax credit of up to $35 per ton of CO2 if you capture anthropogenic CO2 and use it for enhanced oil recovery. And if you use it for direct storage, you can get up to $50 a ton of CO2. Those now are numbers that are high enough that they become interesting. All right. So one of the things that I did with one of my former students did. Okay, as always, you know, my former student did all the work, just like my current students. I just tag along and try to learn something. This is a fellow named Ryan Edwards, who thought about how this tax credit might be leveraged to build large-scale pipelines that could connect sources of CO2 to sinks of CO2. All right, and he asked, thinking about the fact that the low-hanging fruit are the industries where we don't have to do gas separation. Okay, so he mapped out here on this map different sources from which the exhaust gas is pure CO2. And it turns out that if you just look at this, natural gas processing already turns out to be connected. These orange lines here are existing CO2 pipelines. So these are the main current anthropogenic sources for CO2 EOR that doesn't use natural sources, okay? But what you see is the map in many ways is dominated by these clusters of green, which correspond to corn ethanol, which of course, environmentally, corn ethanol is not a good idea, but it exists in the US for various policy reasons. The shaded areas here, these sort of, the yellow shaded areas, indicate locations of potential storage. And you see there's a whole cluster of easy to capture sources in the upper Midwest that don't sit on top of any storage geology that would work. All right, so Ryan asked the question, is it possible with the 45Q tax credit to have enough money in the system to make it profitable to build a pipeline that would take captured CO2 from this cluster and deliver it down to West Texas for enhanced oil recovery? That's the question. Economically, does it work? And in other ways, could it work? So we wound up writing a paper on this, published in late 2018. I'm more than happy to send it to you if you're interested. The upshot is that you can wind up designing a pipeline where, with modest assumptions, you can achieve economically feasible results so that investors in the pipeline can get a reasonable return and the emitters can have a net increase of profit by capturing the CO2, paying the tariff to use the pipeline, and then in this case selling it to EOR users, in this case in West Texas. So the economics for this seem to work out. Ryan was sufficiently interested that he spent last year as a congressional fellow in Washington in the US Senate, working on legislation to try to make this happen. and he's now actually trying to make this pipeline be built. So in the U.S., I gotta watch time here. It's also an interesting political story because there's political will from both Republicans and Democrats, which is highly unusual these days, and they all have their individual reasons. Okay, but there still seems to be a political will to make this happen. Now the challenge is to think about the much bigger sources, which is the power sector. The total emissions here are something like 30 million tons of CO2. Oops, sorry about that. I'll just do it this way. Per year. All right. You know, the power sector from this part of the country is 10 times that. So I have another student, Yiheng Tao, who's currently trying to think about the power sector, where we're asking the question, if this alum cycle, which I mentioned earlier, turns out to be as good as advertised, and we can think about replacing coal-fired power plants, which are now each of the dots shown on this graph, with an alum cycle gas-fired plant, will the economics work out? And what other policy instruments do we need to make that work? So we're thinking about two levels of large-scale infrastructure development, which means the infrastructure that will allow CO2 sources to be matched with CO2 sinks. And if all of this can be spun together, then I would say there's a realistic possibility of a CCS industry actually beginning in the United States. So that's what I see as a hopeful sign coming from the United States, even with this administration that is very much anti-climate change. All right. So the second one I want to talk about is India, and I'm going to not say much about China because the time is passing, and I'm aware that I should keep within 30 minutes. India is an interesting story for a completely different reason. The only large-scale onshore storage formations that have been identified are associated with this enormous basaltic group that's called the Deccan Traps. And you can see it extends over a significant part of the country. What's interesting about basalts is that they tend to be highly reactive when carbonated brine or when CO2 is introduced into the system. So you get a sequence. I'm not going to go through any of this. Those of you who are chemists can go ahead and explain it to yourselves or whatever. But you wind up with a bunch of calcium and magnesium and other things that will dissolve and then will precipitate out as carbonates. So you wind up with this kind of precipitation activity in what's called mineral trapping. And it happens on a relatively fast time scale. So we're interested in how we can take what looks to me like fairly involved chemistry, put it into what's already a complicated two-phase flow model that includes, you know, buoyancy, mass transfer, convective mixing of dissolved CO2, et cetera, and put all of this together in a framework that allows us to think about exploration of parameter spaces and uncertainties and a whole variety of things like that, that always makes us think about how we can do efficient calculations, all right? And this is the work of Tom Postma. Some of you at Delft will remember Tom, I hope. You were kind enough to educate him really well, and he's now come to Princeton for a PhD and doing fantastic work. So our approach is one that we've used for a long time. This again is a slide I've borrowed from Ruben and his group because it's a great slide. But as you inject, right, if this is the injection well here, you get a plume that basically comes out more or less symmetrically with the light CO2 overriding the more dense brine. So here's brine. This pen is not working very well. Sorry about that. That's supposed to be brine. And here's the CO2. All right. And then post-injection, you just have buoyancy that allows the CO2 to go up dip while leaving behind a residual CO2 zone and developing this miscible dissolved CO2 zone in the brine, which is the blue here, And because of the density difference, you get these sort of convective mixing fingers that give you enhanced mixing in the zone. Anyway, all of this can be modeled. We're basically using what Sarah Gazda had done, along with Jan Nordbotten, with me again tagging along, not doing much, to basically break the vertical world here into just 3 zones: the mobile CO2 zone, the residual CO2 zone, and the brine zone with some amount of CO2 dissolved in it. All right, and when you do that, you can let me see what's happening. Yeah, so you can then break the world up, where you only have to figure out how much of the CO2 is dissolved in the brine. That's sort of down in the blue part here, and then if I have an interface here and an interface here, right, where those interfaces are, that's these 2 gamma R and gamma M, and then I need to get one pressure value. Typically, we take it along the bottom, and we make an assumption of vertical equilibrium with buoyancy involved, and we get a set of reduced equations that allow us to solve all of the flow physics, including dissolution. All right, and what Tom is doing now is to take this framework, redo it to add some extra sort of things that we needed to add, and then layer into it a whole set of chemistry that we can simplify, in the sense that right now, I hope, we can only look at sort of homogenized chemistry in each of these vertical regions, a maximum of 3 regions. Okay, so that both the flow part, which we know is easy to solve in this framework, and we're hoping the chemistry part can be made efficient enough that we can look at a lot of possibilities, because we are data scarce in regard to characterization of things like the Deccan traps and other formations that have not been studied extensively. But we still want to try to see if we can get a 0-order estimate of whether or not there's sufficient capacity in these Deccan traps to make CCS a viable option in India. That's really a high-level question, and we're trying to use a suitably simplified but still complicated enough model to answer that question. And that's how Tom spends his days and nights these days. All right. In China, since I don't have much time left, I only put 2 slides up here, and this is just.
Mark, you could take 10 minutes. That's fine.
Okay, I'll take 5 minutes, and then if I can add more to questions. But
sure.
I always say 5 minutes, and I may wind up taking 10 minutes. So there you go. You never know. There's been some work done in China. Okay, so there are candidate formations. I think it's fair to say that there's been substantially less work done than has been done in the United States, and perhaps North America more generally, the US and Canada. The capacity studies are less detailed. The last 2 points are the ones I really wanted to make. I didn't put a map of China. I took it out to try to keep to the 30-minute limit, but the philosophy of China right now, or the approach, is to focus on solving air pollution problems in the eastern urban areas, Beijing, Shanghai, etc. All right? They want to solve the air pollution problem. And the way that's being done is to the extent possible, move coal-based activities from the east of the country to the west. Okay, and you can see this in 5-year plans and documents and all sorts of things like that. Now, that is already solving some of the air pollution problems in the east. How the coal winds up being utilized in the west will say whether or not there's a corollary benefit for CO2 or it makes it worse. All right. One of the interesting things is that one of the western provinces is the province of Xinjiang, which, if you follow the news, right, has lots of political news these days. But it's interesting because that's a location where 2 major basins and a sequence of formations have been identified with a collective capacity of 30 or 40 gigatons. So it's not a small amount, and it's a place where it seems to us, CCS has a reasonable chance to start. And that province is largely a desert. And it turns out the price of water there is quite high. So this is an area where we've been interested in whether or not we can combine CO2 injection with brine extraction, solar-driven desalination, and then sell the water to make the economics of the whole system work. All right, so it's a part of the world where it looks like this idea of carbon, energy, and water can come together in interesting ways, and the economics look like they might work out to the extent that we have data on that. Okay, the last thing I wanted to say is that if you don't know, China has this really interesting thing that's called the Belt and Road Initiative. It's an enormous development project of international funding coming from mainland China to many other countries. And we've been interested for the last couple of years, I'd say, in whether or not the Belt and Road could be used as a vehicle to export and begin to influence the way that energy infrastructure is developed, and in particular, as a subset, or as a sub-question, does CCS have a role to play? Is there any evidence that CCS is being considered? All right, so we just finished a study of the Belt and Road, and the paper just came out a few days ago. Anybody who's interested, I'll be happy to send it to you. So this is with another one of my graduate students, Yihang Tao, who, this is one of the graphs. This is the only graph I'll show you, because we were interested to ask the question, if we look at what's happening in regard to Belt and Road activities as we define them, what does the energy infrastructure look like? So the Belt and Road Initiative was announced by President Xi late in 2013, which is what this red line corresponds to here. So this is the Belt and Road started from here, BRI, Belt and Road Initiative, all right? Before that, there was no Belt and Road. So we were interested, first of all, in what's happening in regard to energy development in these countries outside of China that are being supported by Belt and Road, and was there a change in the way the infrastructure is developed after the Belt and Road was announced and initiated? And the takeaway message here is that up until middle of 2019, which is the data we've had, coal dominates the entire landscape. That's coal. Right, this is gigawatts of installed capacity. So it's followed by gas, and the only renewable of any significance is hydro, which is down here in the blue. All right, wind, solar, and oil are pretty much down here in the noise. So there are two things we took away from this. Number one, despite the rhetoric, there seems to be no greening of the Belt and Road. I hope we're wrong about that, and in a year we'll be proved wrong. But up until the middle of last year, the data indicated that. And the second is that there's no consideration at all of CCS, despite the fact that we have these enormous new construction of fossil fuel-based plants, largely coal-based plants. As far as we can tell, there's really no thought about CCS as a possibility. So that's not a very good conclusion, but that's what we see in the data. All right, so where do we stand at the moment? President Xi, President Trump, President Bolsonaro, and Prime Minister Modi, arguably from a climate perspective, the four most important leaders in the world. So China, US, Brazil, and Brazil is about deforestation, something I haven't talked about, but I'm happy to talk about. What strikes me is the following, that you might recall that the last Conference of Parties, this annual UN organized meeting to talk about climate, was in Madrid in December of last year, a few months ago. And I found this quote from the BBC interesting because I'm specifically interested myself in my own research in these four countries. And this is what I quote from the BBC, supported by the European Union, thank you guys in Europe, okay, and small island states, comma, the push for higher ambition, meaning relative to more ambition in terms of solving the climate problem, was opposed by a range of countries, including the US, Brazil, India, and China. Exactly the 4 countries that we're interested in, okay, that we need to be interested in. So this makes me pessimistic, I have to say. However, the other thing that happens, at least up until a month and a half ago, when the COVID virus knocked us all out in some sense, are a really interesting set of social movements. This, of course, is Greta, along with Arnold Schwarzenegger. In case you don't recognize Arnie, everyone recognizes Greta. Maybe no one recognizes Arnie these days. You know, you add to that Extinction Rebellion, which has been very active in Europe, in particular UK, and a very strong, at least in the western part of the world, divestment movement, certainly across universities and many other institutions. So I think that there's a really interesting dynamic going on here where the political leadership seems to be completely divorced, disconnected from popular movements that I think may actually have traction to make something happen. And this becomes a really interesting point in time that I'm really worried will lose its significance because of this coronavirus. Okay, but that again remains to be seen. So I wanted to put this just as sort of an ending that, you know, we've now been hit with this kind of, you know, emptiness. I don't want to call it a diversion because it's disrespectful in terms of the severity of the problem. All right, but from a climate perspective, I think it puts us in a difficult position. Anyway, so I did take 8 minutes instead of 10. You know, I think there's reason for optimism in the US in regard to infrastructure development where the parties involved may not be ones that you think will solve the problem or that ought to be making money by solving the problem, but it looks like there's enough profit to be made that we could build an infrastructure whose result becomes a good outcome, which is the ability for CCS to begin to develop on a large scale. I think there are many more challenges across all of Asia, East Asia with China, South Asia with India, and all through Southeast Asia in many different ways. Continued investments in coal. I hope there will be opportunities with the Belt and Road Initiative. That remains to be seen about whether green financing actually means anything and a whole variety of things like that. And from a technical point of view, I think this reactive transport is a really interesting issue in regard to making CCS viable or not in a major place like India. This sort of political versus social tension, I think, is an interesting one. And I think the last question, just in the last few weeks, has become obvious to me in terms of its importance, which is how is this virus going to affect everything, including decarbonization efforts? You know, if you look at the response from the last financial crisis, it was just an enormous roaring back with much higher emissions getting out of the economic crisis, right? Because the whole idea was to start the economy, forget the environment. I don't know how it's going to work out in this case. It may be that, you know, the virus cyclically stays around enough that you can never really get the economy fully working for the next year and a half. And I don't know if that then leads to longer term structural changes. But like I said earlier, how we come out of this coronavirus episode, for me, will tell me whether I should be optimistic or pessimistic about hitting any climate goals. So I think in many ways, it's a really interesting time to be involved in this, but it also gets me very nervous. So anyway, thank you all for your attention.
Thank you very much, Mike, for the great talk. I give the floor to Sebastian to.
Thank you very much, Mike, and warm welcome from me as well. So I'm trying to read now through all the questions that come rolling in at very fast speed. First, two questions are from Soren Pop. Hi, Soren. Mike, I think the reduction of activity in the present context has led to lower CO2 emissions. I assume, Soren, you're talking about COVID-19. Is there an estimate of this reduction? That's his first question. And the second question from Soren is, we have an estimate of the global emissions for CO2, but is there an estimate of how much CO2 is consumed by plants, by the industry, etc.?
Yeah, so the first one is, I don't know, I haven't seen an estimate, but I would imagine that those estimates will come out fairly soon because you can have a direct correlation by just seeing which industries have shut down. And you could even correlate it in many ways with air pollution if you think about emissions related to coal in many parts of the world. The second one was, uptake. Yeah, of course, vegetation uptake as part of the carbon cycle, that happens all the time. So the only impact of emissions on vegetation uptake is a fertilization effect, which has gone, as far as I can tell, by just casually trying to pay attention to a little bit of the literature. There was a time when there was an idea that the fertilization effect would not be very strong. Then more recently, the idea was, yeah, there's probably some kind of noticeable fertilization effect. And then I saw some work recently that indicated that that may not be the case. If it is, it's not a big effect. Certainly nowhere near the level of emissions. You know, the thing to remember in the natural cycle, of course, is imbalance. It doesn't mean that the fluxes are zero. It just means that we have big fluxes going into the atmosphere naturally and coming out of the atmosphere naturally. And over a long time, you get to a dynamic steady state with the fluxes associated with vegetation being on the order of 60 gigatons of carbon a year, something like that. Okay, so it's a big number, and it's only one of the flux compartments, ocean exchange as well, et cetera. When we perturb the system with anthropogenic emissions, right? So far, it's been the case that about 45% of what we put into the atmosphere stays there, and the rest of it is taken up by oceans and by a land sink. The ocean sink is pretty well understood in regard to the mechanisms. I think it's fair to say that the land sink still is under study. We know it's there because you can do it by process of elimination. If you understand the ocean and you know how much you put in the atmosphere, the rest of it has to go onto land because there's no other place for it to go. But the mechanisms of where the carbon actually gets stored, is it just, trees keep on growing everywhere, and you always get a net sink versus a source? That's not clear. There are recent measurements in places like the Amazon that indicate that overall the Amazon is in the process of switching from a carbon sink to a carbon source, in part because of climate change, in part because of deforestation and other sorts of degradation. So if you get a vegetation is important in the equation, but the important driver, as far as I understand, for vegetation is human-induced land use change. And in particular, if we have large-scale deforestation, especially in tropical forests, you can reach a threshold, at least the working hypothesis is that you can reach a threshold that once you flip, okay, that the rest of the forest is doomed, right? So if you take a place like the Amazon, right, the idea is to deforest the Amazon so that you can grow crops. The crazy thing is that if you deforest the Amazon, you reduced rainfall by up to a meter a year, and you increase temperatures locally by like 3 or 4 degrees C, and you make rain-fed agriculture impossible. So it's the dumbest thing in the world, but it winds up being done. Anyway, you should ask me another question, Sebastian.
Okay. The next one is from Vahid. And he asks, how would the current oil price influence the mega scale pipeline project you discussed for the US, which is a CO2 enhanced oil recovery driven project, and the oil price is very low at the moment, so many of the EOR projects are very challenging to implement from an economic point of view?
Yeah, it's a great question. So of course we struggle with that because everything we've done up until a month and a half ago has, you know, assumed that we had a $60 a barrel price or something like that, and it turns out that the price of CO2, the price that if I capture CO2, the price I would be paid for that CO2 is linked to the price of oil. So whatever. But the point is that yeah, it's possible. You know, if it turns out that this downturn is much longer lasting, downturn in terms of the oil industry, right, is much longer lasting than I expect it to be, then it becomes an existential threat to the industry, right? And then the whole idea that we're going to use CO2 for EOR is nonsense. The interesting part of the story is that in regard to the US, we still have the ability to fall back on deep saline storage because you actually get a higher tax credit for doing the saline storage than you do for doing enhanced oil recovery. And the difference is $15 a ton, right? And if I can sell, you know, the price for CO2 before the crash was about $23 a ton or something like that, right? So I get an extra $15 for doing direct storage versus an extra $23 for doing EOR because I get the sale price for EOR. So the difference is not that big, it turns out. So I think it will work out. My student Yiheng is in the process of doing all these calculations right now, but I think it will work out that we can still propose realistic policy instruments that would be enough to allow direct storage at $50 a ton tax credit to actually work and still be sufficient to sort of catalyze the building of large-scale infrastructure. But yeah, the future of the oil industry in general for me is a fascinating question. I mean, I just saw today, I didn't have time to read anything, but Shell apparently has put out an even more aggressive statement about its move to net zero emissions, including emissions from use of its product, right? And what I read in a headline was that in the next 10 years, by 2030, that they say that their target is to reduce emissions by 30%. I have no idea how you do that without CCS. I do not know how that works without large-scale CCS. So anyone here who works in the oil industry can tell me.
Just to, sorry for interrupting here, but I'm throwing my 2 cents in there. It's really fascinating. And maybe that COVID-19 driver and this existential threat to the oil industry is something that is accelerating companies like Shell, like Total, Equinor, really changing the attitude to diversify even more. And I just happened to be on a phone call with Petroleum Development Oman, who now become a subsidy of Energy Development Oman, and it becomes only a part of Oman's energy portfolio, which is much more driven towards renewable energy, solar energy, wind energy, possibly some geothermal energy, because they all realize that just banking on oil, a lot of companies realize that banking on oil may not last you for the future. In the end, could be closer than everyone predicts. And if they don't take action now, they may not be around in a few years' time.
Yeah, I mean, this whole story is so fascinating. I mean, if it weren't so scary, it would, you know, it would be really interesting. But I mean, just think geopolitically in terms of Saudi Arabia and Russia, right? Mm-hmm. I mean, just take 2 countries that depend so much on hydrocarbon revenue, and it's an interesting story. So anyway,
so
yeah.
Going back to the next question from Adalman. How about additional CO2 emissions from making storage happen, building, running, operating infrastructure? Is that already pre-subtracted in the figures? Same for carbon capture and storage for enhanced oil recovery, which results in extra fossil fuel use. So how does that influence CO2 emission budgets?
Yeah, those are great questions. These are all great questions. Those are 2 separate issues. One is you do have an energy penalty. Well, it depends on, so if you have to do gas separation, right, then you wind up with a significant energy penalty of, you know, a few tens of percent, up to like 25-30%, because you have to spend extra energy to do the separation process and all the other sorts of things that go along with essentially building a chemical engineering facility. For the easy capture, right? The pure stream CO2, you don't have to do the gas separation, so you pay much less of a penalty. And then the only thing you need to do is you've got, of course, you got to run pumps along the line of along the length of your pipeline, and so you do, of course, have to pay what amount to operating costs. From a life cycle analysis, you could put in, carbon footprint of the construction process, the materials, et cetera, but it's the gas separation that usually winds up taking a big chunk of an energy penalty. Now, in regard to EOR, that's a really, that's a great question, which is, hey, well, you're putting CO2 underground, but you're just producing oil. So aren't you just trading off, a barrel of emissions for a new barrel produced? And it turns out that that most analyses that I've seen, I've not done the analysis myself. Okay, this is just what I hear from people and what I see, is that you wind up with a net benefit of a net carbon benefit, meaning more goes into the ground than you wind up producing when you burn whatever comes out. That argument sometimes is enhanced in ways that you can choose to accept or not, with arguments like, well, hey, if I didn't produce this barrel of oil that involved losing a bunch of CO2 when I push it underground, right? That would have been produced somewhere else, and there would have been no carbon going underground in that case. Okay, then that gives you, of course, a different way of thinking about the fact that to produce a barrel of oil, it's better for me to push CO2 underground to do it than to just do it in the normal way. Now, the counter argument to that is, maybe if you didn't produce it by EOR, nobody else would produce it. Okay, so depending on which of that second piece of the argument you choose, you get either stronger or less strong benefit in regard to carbon, but you always wind up with some net benefit in regard to overall carbon budget, from what I've seen.
Thanks. The next talk is from Anne Pleymakers. I hope I pronounced it correctly. Thank you, great talk, Mike. With CCS, one of the first storage mechanisms is about CO2 dissolving the reservoir fluid. With CO2 enhanced water recovery, is CO2 driving out the brine. How does this work? Is it about injecting large amounts of CO2 that are then partly produced again, or is it related to the timescales of dissolution versus the timescales of production?
Yeah, another great question. There are two ways we've thought about this. One is, let's try to be clever and use the pressure support from the injection to help the production. And this is some work that we published jointly with a group at Lawrence Livermore a couple of years ago, led by a guy named Thomas Buschek, who was really keen on this idea and did all kinds of great simulations about how you can design, concentric rings of wells that when you get a CO2 breakthrough, they then convert from brine producers to CO2 injectors, and then you carry on, and was thinking about not only getting mass, meaning water or other things out, but thinking about getting heat if you're deep enough, for some kind of geothermal activities and all sorts of things like that. So you can think about these kinds of coupled systems in a dynamic design framework, right, where you have these sorts of things. The other way we thought about it, once we sort of went down that rabbit hole, we sort of came out the other side and said, well, look, we could also just look at the economics as, I'm not going to assume necessarily any pressure support from the CO2 injection, and I'm just going to produce the water for an economic reason. All right, so those are the two limits, and in between, but you can think about how far away you need to be in order to have a useful lifetime of a production well versus how close you want to be to take advantage of pressure support, right? And that led us to two different approaches, one of which was this complicated design, recursive kinds of, concentric rings, and with some of them producing and some of them injecting, and the other was to just sort of say, let's just look at the water economics more or less on its own for the case of Western China.
Next question is from Dennis Voskov. Thank you for the talk. Enhanced solution chemical reactions are very sensitive to the scale of representation. How predictive can a model be in large-scale vertical equilibrium assumptions?
I will. I'm very tempted to take my professorial get out of jail card and say, I think Tom is on the call. He's doing the work. Let him answer the question. But anyway, so he can chime in if he wants. But yeah, of course, that's an issue all the time. And the answer is I don't know. There are timescale arguments, of course, that we'll have to make, and assume that some of them are okay. The way we're doing it now, let me go back. Tom, you can correct me if I'm wrong, but I'll tell you how at least we're, where is it? Yeah, so how we're thinking about it is, you know, if I think about things like these dissolution fingers coming down here, right? That when we define this omega up here, which is the fraction of brine, so this is explicitly, this I cut and pasted this from a document Tom put together, that's saturated with CO2. So, you know, at least what we're doing is saying that when I look at the brine, right, I'm not assuming I just have one average concentration where 50% of the brine mass is, or you know, the concentration across the entire brine mass on average is 50%. You know, we're thinking about the fact that these kinds of fingers tend to have high concentrations of the dissolved CO2 in them, in this case, all right? And so we'll think about these, the area blue, the blue area here as kind of one domain, and the white area as a second domain, and the reactions only take place in the blue domain. All right. Now, that assumes that the spatial mineralogy of the rock that this blue finger is encountering, with its lower pH that's driving whatever it's driving, is relatively spatially homogeneous, and a whole variety of things like that. So the answer is, I'm hoping that we'll have an argument that is defensible, that says you should at least think our calculations are good enough to answer the large-scale question that we're interested in. You know, the thing that, in my mind, where the scaling issues that you raise are going to be important is that the specific question that we're interested in, at least that I'm interested in, is, will there be locations where you get excessive precipitation of new minerals that wind up reducing the permeability so much that the injection becomes difficult, right? Because you've got a precipitation, a dissolution precipitation sequence going on, and you know, you can even, there have been two sort of significant field experiments done with this system. One was in Iceland. Some of you, I'm sure, read about it. The other was in the Pacific Northwest. But you know, in the Iceland case, if you read the paper, there'll be a statement in there that says something like, "Well, they did very sparse measurements, but they had a statement something like, we assumed, or we imposed continuous in time injection." And that meant that we were always sort of pushing a dissolution front, and then later on a kind of precipitation activity. But you know, if you imagine a sort of pulsing or any interruption of the injection activity, then you might wind up with clogging issues. That remains to be determined, and things like that. So there are sort of large questions, I think, like this, that require some kind of an analysis of scaling that we hope we can hang our hat on to at least make a first kind of zero order estimate. That's the best I can give you as an answer.
This is not a question, it's a comment. I'm just jumping around a little bit from John Ludden, the former CEO of BGS, British Geological Survey, comments that basalt reactivity is an interesting one. The early results do show faster reactivity than anticipated. We need to move to a pilot which involves a variation of the geological seals and leakage to reassure populations living over these potential storage areas. So that's pretty much, I guess, what if you get your models to work, Mike, what we can do and support these pilot studies. Let me just scroll back to the next question. And Hadi, you're going to tell, you're the boss here, you tell me when to stop asking Mike all these questions. We have one from Ari Eftikari who says, CO2, although very stable molecule, can be reduced to fuels using hydrogen from electrolysis driven by wind and solar electricity. Do you see a future for CCS in smaller scale, at the smaller scale as a feedstock for fuel production in the future CO2 recycling scenario?
Yeah, of course, that would be great if we can use excess renewables to drive some chemical, effectively a sort of chemical storage of energy that we can then go use to make something useful out of a waste product, which is CO2. I just don't have a sense of how realistic it is in regard to scale, right? So if I need to get 10 gigatons a year out of the system using some version of CCS or some version of a capture, all right? Is that order of magnitude of mass of CO2 remotely feasible to be processed? Is there? So I haven't done the calculation, but it seems to me one could do a kind of straightforward energy a calculation of how much excess renewables one imagines being able to capture over a monthly timescale, for example, and the efficiencies with which you could use that to convert CO2 into fuels, and what that implies about the mass of CO2 that you could sort of feasibly process, and then whether or not there's a market for the fuel that you're producing, and a whole variety of things like that. So I think there are a lot of possibilities like that that are being explored, some in the context of direct air capture or other sorts of things, and if they work out, I think it'd be great. It's one of these things that I think remains to be seen.
We have a question here from Majid Tassanizadeh. There have been ideas for large-scale direct capture of CO2 from the air via geochemical reactions, for example, using the use of olivine. Could you comment on that, please?
Yeah, thanks, Majid. I think I would sort of stick by the comment I made in passing, which is when I just think about the length scale of a machine that one needs to build to capture significant amounts from an airstream that's 400 parts per million. These things become gigantic, just enormous. You need to have materials that you don't get armoring at the surface, so you get a surface reaction and then you're done, and then you have to go build a mountain of some reacted olivine or whatever it is. And so every time I think about these things, and I'm sure it's because I don't know nearly enough on the topic, it just strikes me that the engineering aspects of doing this are just overwhelming. And I know that there are people like David Keith who has started his own company to do this and is very bullish on it, and I hope he's right. I really do. But it just seems, I mean, if you just give me a choice, capture CO2 out of a 400 ppm stream or capture CO2 out of a 10% waste stream, I'll go for the 10%. It's coming out of smokestack. Here it is. It's being delivered to me. I don't have to capture it with a building that goes over 100 kilometers, right, in the horizontal direction. It just makes more sense to me to think that I would capture from the more concentrated stream. Nonetheless, direct air capture is certainly much more popular than capturing from a smokestack, and I'm not really sure why that is. Maybe it's because direct air capture is kind of a new thing relative to capturing something from a dirty smokestack. And I guess direct air capture can take place anywhere in the world, so that's of course another benefit. Anyway, the answer is, Majid, I every time I think about how to engineer this thing, it just overwhelms my feeble brain.
Thanks, Mike. We have about 5 minutes left for questions. So I'm just going to try to, with apologies to all the questions that still keep coming in, I'm just going to read off a few more questions and hopefully Mike can answer them quickly so we get as many questions asked. So there's one that I found very interesting from Huub Doma. What if hydrogen storage will take off for the hydrogen economy? Would that have a big impact on storage capacity for CO2?
Not sure the question means, would we think about storing hydrogen underground? Is that the issue? Or
I would say probably on I interpret it as generally the CO2. Sorry,
I missed it.
Yes, underground storage
of hydrogen. Yeah. Yeah, there it's just a question of whether or not the confining layer is good enough to keep the much smaller molecule in place. But certainly it's something that different groups are looking at and thinking about. So I it's another way to for me, it's part of this whole list of ways that we should be thinking about how subsurface can be used to solve energy and climate problems. And it could be that things evolve so that we're storing hydrogen instead of CO2 underground. We need the same kind of characterization. We just have to realize that it's easier for the hydrogen to escape and make sure the confining system works.
We have a question from Hadi Bakbidar. What's the best strategy to choose the best source of CO2 emission for CCS? Based on CO2 concentration, choose based on the amount of CO2 emission in a region? Any other points?
Yeah, at the end of the day, I'd say that no matter what I think, the choice will be made based on what the economics say. So if it's cheaper for me to capture from a dilute stream, like a power plant, because I have a pipeline running in my backyard that's already been paid for by somebody else, and therefore the tariffs I have to pay are low, then I might do that. Or if I'm sitting on top of a saline aquifer in the middle of the Illinois basin, so that I don't have to pay any tariffs to use a pipeline, I can just put it underneath me straight away, then location might be the most important thing. But in general, I would say if we're only interested in capture, the way I think about it is the sources that have a pure CO2 stream coming out of them are the ones that I would look to first, because I don't have to do any separation. I just capture what's there.
So I'm going to do two more questions. One is from Omar Emmanuel Godinez Brizuela. Name is almost as long as the question here. The economic viability of CCS seems highly reliant on tax credit. How certain is it that these tax incentives will remain in place in the longer term?
Yeah, another good question. So the tax credits are going to expire 6 years after 2018, so in 2024. And so there's general recognition that either the Congress extends the tax credits, or this really won't have much of an effect. I think in 2 years ago, in 2018, there was a bit more optimism, but for whatever reasons, the rules for what it means to have this tax credit and how it would actually work, which come out of the Treasury Department of the U.S. Okay, those rules were not even proposed until just a few months ago. So there was all sorts of delays for whatever reasons, political or otherwise. So this would clearly need to be extended in regard to its applicability in order for this to happen. But again, because there's this bipartisan support, right? The Midwest states are interested because they want to keep an otherwise not so good ethanol industry going. For example, if it involves ethanol, oil producing states are interested, meaning, and all of those tend to be Republican states. But from representatives interested in solving climate issues, which tend to be on the Democratic side, they're also interested in practical solutions. Okay, so you get this interesting mix. So I would say the prospects are pretty good for a political extension until the time when we may get a more comprehensive carbon emission tax.
So in the last question, I award to your former postdoc Florian, who's also wins the prize for the best COVID-19 haircut in this.
Excellent.
And he asks, I think, a really interesting question. Prior to the economic crisis in 2008, there was a big ramp up in CCS. And over the last 2 years, that CCS has been reinvigorated. And as you said, there's a lot of political pressure now. How do they compare to each other?
Yeah, that's another great question. It's a fantastic set of questions. That's sort of what underlies my comment that I made, that what happens in the next couple of years, I think, will tell us what's going to happen with the climate over the next 20 or 30 years. Because as Florian points out very correctly, prior to the financial crash, 2008, I'll just speak in regard to the US. There was a broad expectation in the US that legislation that was moving through the Congress would be passed to put a price on carbon emissions. Every oil company was developing a carbon services group, at least every one that I know of, and there was just this expectation that that's what was going to happen. And somehow the financial crash comes along, and everybody's attention gets diverted, and we come out the other end, and then there's a realization that maybe we don't really have to do anything. All right, and the whole thing just kind of disappeared. All right, and then along comes the Paris Agreement, which gets emitters or oil producers or whatever a little bit nervous that something's going to happen. So that now has motivated the reactions that have been taking place that I think Florian is referring to up until a month or two ago. My own observation is that while there has been renewed interest in CCS, it's a bit more tepid than it was 12 or 14 years ago, when I think there was just a general expectation that we had to have a big CCS industry. So how we come out of this coronavirus, and whether or not there are still these strong commitments for emission reduction from the business sector, including the oil industry, or whether or not when we come out of this, what we're greeted with is silence. That would be, for me, a main indicator of what's going to happen as we go forward. The last thing I'll say, though, is that, again, I'll repeat that I would like to hear somebody else's ideas here, because if I think about, BP announces that by mid-century, they want to be carbon neutral or 90% there or something like that. And they're including what they call scope 3 emissions, which is the emissions associated with use of the product, meaning what comes out the tailpipe after you buy the gasoline. It's not from their facilities, it's from use of their product. The only way that I can imagine that happening is that as a company, same with Shell's announcement today, but as a company, you are assuming you're going to put more carbon away than your customers are going to produce, right? And I assume that means an underlying assumption that you're going to be part of a major carbon capture and storage activity, which means there has to be a large CCS industry. Is there any other way to do proper accounting other than everybody buys the same tree that gets planted somewhere in the world? But it seems to me that I don't know how that works without CCS. So if somebody has an idea of how you can claim that you are carbon neutral if you're producing a hydrocarbon, and what comes out of the use of the hydrocarbon is included in your accounting, how do you get the negative part of that ledger to balance out all the positive part? I can only think of CCS.
Okay. Thank you again, Mike, for yet another very inspiring talk, and thanks to all the participants for excellent questions and discussion. Please note, the webinar will continue next week, the same time, the same hour. We are going to again get together, and the speaker will be Martin Blunt from Imperial College. And please try to attend, because just seeing you all in these moments of working from home is just nice. The record.
Can I just say, Hadi, that I want to thank you actually for the invitation. Sure. Thank everybody for the questions and for joining here. It's a lot of fun for me to talk about these things, and like the rest of you,